Previously, we had looked at the plane wave solution for Maxwell's equations in a source-free region, in a source-free setup. Now let's take the look at, call this the Phasor edition. So we'll look through this in the form, through the lens of viewing these sinusoids as phasors. Recall that our general form for Maxwell's equations, which we, in a source-free region, which once we defined electric field is in the x direction only and magnetic field is in the y direction, we end up with the second order differential equation for E, and then also something similar for H. And we decided that we would call, so the solution would be a forward and backward propagating wave, and we just wrote them out as a generic sinusoid, right? So the instantaneous form of E of zt is going to be equal to some amplitude cosine of frequency and time, frequency and space, and a phase, plus something going in the opposite direction, right? So frequency and time, frequency and space, but same sign now, not different sign, and some other phase. So now let's rewrite this in phasor form, right? So we can look at the phasor form. We'll look at just the forward propagating wave portion. So the forward propagating wave, I was calling the forward F and the backward Z. F of zt, if we were to rewrite it in phasor form, we would expand this and say this is also equal to the real part of the amplitude e to the j phi 1, e to the j kz, or minus jkz, e to the j omega t, right? Basically e to the j, all of the stuff that's in here. But what we ended up doing is to call, when we're doing phasors, what we do is we take this real part and e to the j omega t, and we say, all right, we know that we're going to just take the e to the j omega t and the real part, right? If we have a phasor, e to the j omega t is basically rotating this in the real and imaginary plane. So in this case, all we're going to do is we're going to track what it is at t equals 0, right? It's going to be some amplitude and some phase. And we have the solution to that. That's the solution at t equals 0. And to find the solution for any other time in t, we just start the clock and start rotating this, right? We multiply by e to the j omega t and track the real part. So we just recall when we're dealing with phasor analysis, what we do is we just ignore these parts for now. Just deal with this, which is just a complex number. And once we have the solution, if we wanted to find what it is instantaneously at any time t, we just slap that e to the j of omega t back in, add in the real part, and then voila, we get the final result, right? So when we look at it in this way, one nice thing that happens is, since you're only looking at this complex number that's in the form of some magnitude e to the j something else, a time derivative with respect to t, note there's no t here, so a time derivative, if you know your answer is a sinusoid, a time derivative is the same as multiplying it by e to j omega, which means that our Maxwell's equations, if we were to bring the curl expression back, these used to be time derivatives, they're just now minus j omega. And then we still have mu here, epsilon here, e, h. And then the divergence is still 0, so that's not affected. So you'll recall when we introduced Maxwell's equations, we had a phasor form of a source free, which is where these came from. So we made this phasor assumption, redefined the time derivative as a multiplication by j omega, and then just kind of plugged it into Maxwell's equations as we knew it. So now what I'm going to do is, similar to what we did with the Tolographer's equations, we're going to do a little bit of manipulation and see that E and H have the same relationship, a very similar relationship to what we have with V and I, with the voltage and current, and the characteristic impedance Z naught. So remember, our Tolographer equation or transmission line cheat sheet is we're just substituting the letter E with the letter V. For magnetic fields, we're substituting H and I, and epsilon would be similar to C, and mu would be similar to L. And again, this isn't necessarily saying there's a direct physical analogy with these quantities. We're just saying the math expressions look exactly the same if we do these letter substitutions. Therefore, if you understood the derivation before, a similar derivation works here. So let's do a vector calculus version of the Tolographer's equation derivation. So recall what we did for the Tolographer's equations was we took the spatial derivative of both sides. In this case, we're going to take the curl of both sides to get 2 curls of E is equal to minus j omega mu curl of H. I'm going to use this identity that we have in vector calculus that we're just using it this one time, so no need to worry about it anymore than just showing it here and seeing that this is true. But I'm just going to pull this out of my sleeve, use it, and then we'll move on. But this is a vector calculus identity, which can simplify this double curl of E expression. Note that because we're source free, so this is actually going to be 0 since the divergence of E is going to be 0. And so you have the expression that the double curl of E is going to be equal to minus the double gradient, minus del squared E. And we also can substitute that del cross H is going to be equal to j omega epsilon E. So substitute this on this side, this into the other side, and you get this. So you get del squared E is going to be equal to k squared minus k squared E. And this is the Helmholtz equation. Our familiar friend here. And so the solution of this will be plane waves. If we plug in our Phasor definitions for E and H and do some manipulation, I think that's probably enough detail, and I just want you to look at the final result to gain the intuition. But you will end up by comparing the two in Phasor form and doing substitutions. You will find that you'll find this Phasor expression for the electric field. So no surprises here, some magnitude for propagating wave because we're multiplying by e to the j omega t. So opposite signs, this is a forward propagating wave and a backward propagating wave. If you plug this into Maxwell's equations and substitute back and forth, you will find that h of z is going to be equal to the forward propagating wave divided by eta e to the minus jkz plus backward propagating version eta e to the positive jkz. Oops, I made a mistake here. Recall that again, this looks exactly similar to the transmission line equations, and in the transmission line equations we found that when we were trying to relate the voltage and the current, you have a sign difference, right, if you were in the negative propagating direction. So let me just add to this, but we're going to substitute this eta is mathematically similar to what we were calling z naught, which was square root of L over C. And in this case, eta is going to be equal to mu over epsilon. So I'm kind of bearing the lead here, but if you were to substitute this into Maxwell's equations and run through the equations so that they're self-consistent, you'll find that for it to work out, eta has to be equal to mu over epsilon. For free space, eta naught, which is equal to the square root of mu naught over epsilon naught, is going to end up equaling 120 pi, or about 377 ohm. So you can kind of view this as like the characteristic impedance of free space. So again, this is what, in Phasor form, how the electric field and the magnetic field will relate. So if you were to change the electric field, if you had the electric field and you wanted to know what the corresponding magnetic field would be, the amplitude relates to each other by a factor of eta. if it's going in the positive z direction, or minus eta if it's going in the negative z direction, or eta with a pi phase shift. And secondly, the other thing to remember is that the definition of eta is going to be equal to mu over epsilon. Now, one other thing to keep in mind is that this is the part that's a little bit different, or a little bit more nuanced than transmission lines, is in this case, while your E is in the x direction, if you divide it by eta, that doesn't just give you the magnetic field by itself. You also have to make sure that the magnetic field is in a direction that's perpendicular to both E and the direction of propagation. So in this case, we know it's propagating in the z direction. We know E is in the x direction. So I know the magnitude, I just divide by eta or negative eta, depending on what direction it's propagating. But if I needed to find the magnetic field, I also need to know that the magnetic field is in the y direction. And I get that by making sure I choose H such that E cross H is going to be equal to the direction of propagation. And that is another reason that you see in this negative sign too, right? In order for this to work out, if E is in the positive x direction, H needs to be in the negative y direction in order for E cross H to be equal to negative z, which for a backward propagating wave, the wave would be in the backward propagating direction. So in general, the main trick I want to get to is if you have the E field and you want to get the H field, or the other way around, first of all, the magnitude, E magnitude is, the magnitude of the E field is going to, over the magnitude of the H field, is going to be equal to eta. And second, the direction is such that E cross H is going to be equal to the propagation direction. So with transmission lines, we could just use Z naught to find out how V and I correlate, respond to each other. But separately, you also need to know, if you know the direction of E and the direction of propagation, or two of the three, if you know the field of one and the direction of propagation, you need to choose the direction of the other one, the polarization of the other one, such that E cross H equals the propagation direction, such that that relationship holds. So as a quick review, we re-examined these equations in terms of phasor form, and by I mostly was just kind of wanted to outline the process to result in the Helmholtz equation. So this is kind of like the 3D vector calculus version of the wave equation solution that we were solving in the past. The solution is still a backward propagating wave. And if you define the electric field and plug it into Maxwell's equations and make sure that they're in order for the terms to make sense as you go from E to H and then back to E, you're going to find that the E field and the H field are related by a factor of eta, which is our equivalent of Z naught, our characteristic impedance in the case of plane waves. And eta is going to be equal to the square root of mu over epsilon, which is kind of in our word substitution game, it's the same as characteristic impedance being the square root of L over C. And the other thing to note is that if you had, say, the electric field and you want to find the magnetic field, the magnitude is related by a factor of eta, but you also need to figure out the polarization of the unknown field, and you have to choose a polarization such that E cross H gives you the propagation direction. And while we're in the process of, just to wrap up our review of key constants that are important, remember the propagation velocity is equal to 1 over the square root of mu epsilon. So naturally, 1 over the square root of mu naught epsilon naught is going to be the speed of light, c. And also our wave number is going to be omega over c, which is omega over the square root of mu epsilon, which is another quantity that we had defined in a different discussion. So with that, you have the key form in phasor form, how you would find E and H relative to each other, and also the definitions of the key important constants of the propagation velocity, the wave number k, and eta.